So this is in continuation with our discussion on input-output subsystems. We were talking about I/O buses and various ways in which bandwidth or the throughput could be increased. So one is increasing the bus width, the number of wires, having separate wires for data and address, pipelining, as we saw in case of AHB light bus, transferring multiple words in a burst. So in HP light, we saw that although you have a burst coming from consecutive addresses, you still need to give addresses every time. But there are other buses which have a different protocol where you give address only once and you can transfer the burst of required length. Then there is a distinction between synchronous and asynchronous buses. Typically, synchronous buses are faster, and possibility of split transaction allows some overlap between different transactions and helps in improving the speed. So let me just repeat this part. The way synchronous and asynchronous buses differ is that in synchronous bus, all transitions happen at certain clock edge. Okay, so here we are showing that the initiator would send a start pulse. Okay, it's a so this is one example only. All synchronous buses may not exactly do this way. So this cycle is being used to send address, and this control signal start indicates that this is starting of the transaction. Then there is a response by the responder or the slave, which is coming at certain fixed cycle. For example, here in this case, it's coming in the third cycle after the address was given. Okay. So white is showing response from the responder, and this orange is showing what is coming from the initiator. So the timings are pre-decided, and everything happens on specific clock edges. In asynchronous bus, all the events happen at independent time. They are not synchronized with any clock. So we took one illustrative example where the initiator is sending a read request. Okay, and at the same time, we are assuming here that there are common wires for sending address and data. So it is sending data here, address here on the data lines, and there is an acknowledgement from the slave or the responder in response to the read request. Yeah, there is noise coming from some mic. Please mute it. After certain delay, which could be arbitrary, the slave sends data and indicates that by a signal called data ready in this case. Okay, so response to data ready is in the form of another acknowledge pulse coming from the master. So the sequence of events is very important. The time interval between various events could be arbitrary. So this is the first thing. After read request goes up, indicating availability of the address, acknowledgement will come from the slave. So there is a causal dependence between these, and this acknowledgement from slave means that address has been recorded, and in response to that, read request goes down, the address may be removed from the bus. So after having seen request going down, the acknowledgement goes down. Okay, so the idea here is that you can't just give a short pulse because you want to give arbitrary amount of time to the other party. So there is no assumption being made here between assumption about the interval between various events. Okay, So this acknowledgement could come after read request at arbitrary interval, and the master would lower this down again after arbitrary interval. So this is called handshaking or interlocking. The, the purpose, yeah, this one. The purpose of this is to assure that nothing is read twice and nothing is missed out. Yeah, the question now.
Yes, sir. So, like this acknowledgement and the other handshakes, are these edge triggered or level triggered?
These are level. So you respond to a level. So the slave sees whenever read request goes to 1, it knows that it has to respond. So it responds by making acknowledgement equal to 1. Uh, so I'll show a flow chart or state diagram which will indicate how these event sequence is maintained. Okay.
Alright.
So this is the next sequence. So in response to this event, acknowledgement going down, uh, the slave works on it and responds with data after some time and indicates that by making data ready. So this is the fourth. Then in response to this is coming. That is fifth dependence. And in response to this having become 1, then this next event is happening. And the last one is this 7th. Okay. So for the next cycle, uh, read request can go to 1 only if this whole chain has been completed. Now these are the state transition diagram of how the sequence is controlled from the initiator side and the responder side. So normally initiator is in this state. When there is a uh, okay, sorry, you could say that when new request is there, when initiator is in a position to make a new request, it starts with this state. So this is starting state. And it has to ensure that you proceed further if acknowledgement from the previous transaction has gone down to 0. Now, I'm sorry, I think I'm missing the order. Okay, sorry. It's that would have been seen actually at this point. So let me start all over again. So in the starting state, when there is a request, uh, you are outputting address and making request to 1, and you're waiting for acknowledgement to come. So as long as acknowledgement is 0, you repeat in that state, and when acknowledgement is 1, you are moving to the next state. Here you can remove the address from the bus, that is bus is released and request is made 0. Then you're waiting for ready to be 1. Okay. Uh, then when ready is 1, you accept the data. So I'm showing a read operation. Data is taken in and acknowledgement is made 1. So you need to be in this state till ready becomes 0. Okay. And at that point you lower your acknowledgement and you are ready for the next transaction.
So, sir, isn't this a clock to circle? How is asynchronous then?
It is asynchronous because there is no common clock in this. Each party could be running its own clock and take any arbitrary amount of time uh, between various events.
Oh, okay, okay. And also, sir, in the second stage, when it says that, so could you go to the next slide?
Yeah.
Here, when it says the address has been released and then request has been put down. So let's say it is not yet ready, right? So it comes to the second state again. But since address has already been released, what is the meaning of second stage now?
Address has been removed from the bus means that would happen if the slave has recorded the address. Address was put on the bus and acknowledgement from slave means that slave has have taken in the address.
Okay, so we don't need it again. So like even if we go to this remain at the second stage, it won't affect anything till then, till we go to the fifth, this third stage.
Uh, yeah, you see, after this thing, you are waiting for, let us see at how many places waiting is required. So it has to wait for acknowledgement to become 1. So seeing from the master side, then it has to wait for acknowledgement to become 0, and then it has to wait for ready to become 1, and then ready to become 0. So this is how the whole cycle will get completed. So here waiting for acknowledgement to be 1, waiting here for ready to be 1, waiting here for ready to be 0. Okay, uh, and then waiting for a new request to come. So on the responder side, again there are different states. So each state indicates that you are waiting for something. Okay, so you're waiting for request here, and then you are waiting for request going down. Then this transition, I've just put a delay here. That means, so assuming that the slave is slow, it needs some time to come up with data. So after this, after some delay, you come to this state where data is given out on the bus and ready is made 1. Okay, then you need to wait for acknowledgement to become 1.
So in the previous diagram, you said that the initiator waits for acknowledgement to become 0, right? Or so data ready, data memory slave. What waits for this acknowledgement to become 0?
This which point?
Earlier,
Acknowledgement.
earlier.
So acknowledgement is a signal which is in this case shown to be driven by both sides. Okay, uh, you could have, I mean, this is not necessarily universal. You could have a separate acknowledgement signal coming from slave going to master, and a separate signal going from master to the slave.
No, I mean, why do we have to wait for acknowledgement to become 0? Why do we wait for that?
Here, yeah,
Yes, sir.
okay. Uh, this acknowledgement going from 0 to 1 is an indication that yes, I have seen, slave is saying that I have seen request going from 0 to 1. Okay, then request going down to 0 means that master is saying I have seen that your acknowledgement has become 1. Okay, then slave going down, acknowledgement going down to 0, it slave is saying that okay, I have seen that your request has become 0. That means I have seen that you have seen my acknowledgement.
Sir, for slave, how does that matter? I mean, slave is still processing the data, right? So for it does not matter whether the request is 1 or not or whatever, because it has the address. It is still processing the data. Sorry, address to
Huh.
output the data. So it will in a processing phase, right? Only when the data ready becomes 1, the slave can say that okay, I have seen this has happened. Because till then it is already working. It does not matter what is going on in the read request, right?
Yeah, well, in this case, it is essential because the same wire is to be used by master. So ACK has to be lowered from the slave side. Okay, and
So,
and to the master, it is an indication that this first handshake is complete.
had there been different signals,
Um,
this lowering was not required.
Uh, lowering, well, eventually it has to be lowered.
Yeah, like
You
at the
know,
end of the processing, it
so
can.
some dependency will get cut down.
Okay.
Before sending the next request, you have to see, ensure that acknowledgement has gone down to 0.
Yeah. Okay.
Okay.
Sir, in the FSM for uh, the master, I
Yeah.
don't think there was a check for acknowledgement being lowered here, right?
Mm, yeah, you're right. So yeah, so that seems to be missing. Mm.
Sir, I think also the data ready will only become one after the acknowledgement has become zeroed by because they are both driven by the slave.
Mm.
So like at that point, so only after the acknowledgement becomes zero will it make the data ready one. So that doesn't matter really.
Yeah, but as I said that before master is able to respond by this acknowledgement, it has to see that acknowledgement signal from slave has gone down to zero. Okay, so actually one could say that it has to wait for uh, two conditions here: ready to become one, and acknowledgement to become zero. So you could sort of combine these two, uh, that this going down and this going to one. Both these are essential before master can uh, do this next activity. Okay, so it could be one could have two different states, or maybe here itself you could have a combined composite condition.
So, but the slave is driving both ready as well as the acknowledgement here. So obviously, like it will be the slave will make the ready one after the acknowledgement has like
Yeah,
after it makes the acknowledgement zero. So
it's
you
a
can just wait for one condition.
it's a question of whether one could make that assumption or not. And you see, one may have to see this in a larger context, that if there are multiple masters, okay, so typically, a transaction which has these two parts which are clearly separated, where address is being given and then data is being received, there is a possibility of making it a split transaction. So in between, the bus has to be completely released for possibly another master to use it. Okay, so whether we can combine these or have to keep these separate has to be seen in a larger context. But just if we were looking at these two devices, uh, it is possible that we make an assumption that slave will ensure that before it makes data ready one, it will put acknowledgement down. So either way, one could work it out. Okay, I mentioned this about split transaction. So the idea here is very simple, that transaction which is split in two parts, begin and end. In between, there is a possibility of releasing the bus. And during that part, it could be beginning of another transaction. So two transactions may be coming from two different masters can happen in this manner. Okay, we looked at uh, this AHB Lite as a parallel bus. This had actually possibility of different number of bits. So parallel buses have multiple wires. Typically, the number is multiple of 8. Okay. Uh, there could be separate wires for address and data, or they could be combined. Those possibilities also exist. On the other hand, serial buses send one data bit at a time. Okay. Uh, Again, the read and write may be on separate wires, or it could also happen on the same wire. Okay. Uh, so it could be going to the extreme that everything is on just one single wire. Address, data, control, everything comes on same wire. So clearly that makes it very inexpensive. So some examples of parallel and serial buses. These are some industry standards. Okay? ISA, EISA, VLB, PCI, AGP. Okay, so different standards have emerged in industry, for different use, and many of these keep getting revised for higher and higher specifications. Example of serial buses are shown on the right. USB, which is very common, Firewire, Fiber Channel, PCI Express. Okay, PCI stands for Peripheral Component Interconnect, and E is for Express. SATA, Serial Advanced Technology Attachment. It's particularly for disk drives. So why do we need serial buses? Why do we want serial buses? So one obvious thing is that serial buses are less expensive, less wires to carry. And another motivation for serial buses is that when you're trying to transfer data at high speed, that means signal has to switch on a wire at a very high speed, then keeping all the bits synchronized in a parallel bus is very difficult. Okay, because of different delays which may be occurring on different wires. And when delays are comparable to the rate at which bits are changing, then this could be problematic. So, but in serial bus, you need to worry about timing of one bus only. You don't need to worry about timing across different wires. So if your wires are long, so that means bus could be there could be a cable which is carrying the bus. So USB, for example, there are USB cables. Okay, so, some buses are internal to the system. Inside the box, you never see them physically. Or there are buses which are on the chip. Okay, so on the chip buses which are off chip but within a system, and there are buses which are going from one box to other box. Okay, so longer the signals, more skew is likely to happen among the bits of parallel buses. So therefore, when there is a question of two physically separate modules or subsystems to be connected, it's typically convenient to have it over serial connection. So there has been a move in the industry from parallel to serial buses. Originally, you have, for example, PCI bus, which was a parallel bus. As you can see that different different versions, there is an improvement in terms of clock rate. There is a parallel arrangement here, 32-bit wide or 64-bit wide. Okay, and you could see that the bandwidth is going up as you increase the clock rate and also as you increase the bus width. Then a serial version of this evolved, which is called PCI Express, and it carries parallelism in little different form. So there could be multiple lanes, but each lane is independent. We do not think of, let's say there is a PCI Express bus with 16 lanes. So this is not same as a 16-bit wide parallel bus. Here each lane is carrying an independent channel. Okay, each is serial one, and they could be independently communicating with different devices. So again, within PCIe, there are evolving standards. Okay, with increasing data transfer rates, and these rates which are shown here are per lane. So if you have multiple lanes, multiply by that factor. Another example is ATA bus, which had been used for disk drive interface. There is evolution in terms of speed which is happening here, but then things change to serial, from parallel ATA to serial ATA, and within that you could see even much higher bandwidths have been achieved. Okay.
So here bandwidth equal to speed of transfer.
Yeah, bandwidth or throughput. I might be using these terms interchangeably.
Okay. So why is serial having the like, much larger bandwidth than the parallel one?
Yeah, see in parallel, you can't arbitrarily increase the bit rate because then the skew problem starts coming in. Right. So if you have 32 byte bus, then 32 each unit of data is 32 bits split across 32 wires, and the rate at which you can change the data uh, is sort of hampered by the skew which is there. So there may be different delays in different wires, and therefore you can't switch them very fast.
So, but still, like in the parallel case, for transferring a 32-bit number, let's say. So, in that case, it will take place within one clock cycle in the
Yeah,
parallel.
one clock cycle parallel bus will take so many bits together.
Yeah, and in serial case, it will take like 32 clock cycles. Although the
Right.
clock
But
duration may be different.
those clock cycles can be very fast. Yeah, it may sound surprising, but that's how it is.
I see, sir. So still it
Sir,
manages better.
Yeah, on the whole, you can have very high speed. See, because of the long wires, you have whole USB cable, and there is substantial delay or skew uh, on the wire.
Sir, so in the clock at which the buses work, is that the same clock at which the CPU is working?
No, these could be independent. Usually, CPU has a much higher clock rate than what would be there on these buses.
But do they have to be like a rational multiple of each other?
No, not necessarily. They don't have to be.
So if that is the case, then CPU accesses data using buses. Then let's say the bus speed is much slower than the
Yeah.
CPU's clock speed. Won't
Yep.
that hamper the processes in the CPU?
Yeah, but there are multiple devices, multiple buses connecting different peripherals.
No, but anyways, for any bus, like it accesses for any bus access, it take more clock cycles than the CPU, right?
Yeah.
So that's CPU clock cycle. So let's say I
So
allocate in the,
typically,
for example, the processor.
from these buses, you would be feeding into the memory. So typically, imagine DMA type of transfer. Okay. So there are, let's say, data going from memory to the graphic display. On the other hand, data coming from Ethernet controller to the memory. So these are happening. You have set up DMA, and multiple such transfers may be going on.
Like so CPU waits till the data comes for that. It
No,
may take
CPU will not wait. CPU will wait for entire IO operation to be over. So suppose you said I want 4 kilobytes of data from this disk, then those 4 kilobyte will come into memory, and then processor will be informed that yes, this whole thing has been done.
So does the processor not use buses for memory access?
It will use for memory access. Yes.
So let's say even when we fetch
Yeah,
instructions from
we'll come to an example
okay.
where you will see all this interplay happening: processor, memory, IO, various buses. Okay, so there is a numerical example at the end, and that will throw some light on how these things are happening. Okay, let me check the time. Okay, so how do you represent bits physically? Uh, they could be represented by unipolar signals or bipolar signals. Uh, you could have an active high convention or active low convention. Active high means that uh, higher voltage level indicates 1 and lower voltage indicates 0, or it could be vice versa. That is called active low. You could have a convention which is called RZ or return to zero, or NRZ, which is non-return to zero. So I'll show little more details of these. You could encode signal using levels or transitions. You could be using one wire for carrying one bit stream, or two wires in a differential form. So example of different ways of representing a bit stream. So you have, let's say, a clock, and the data is a sequence of ones and zeros. So if, now what we are showing here is that this sequence of ones and zeros, how it is represented differently in different conventions by, let's say, a voltage signal. So RZ means that whether it is 0 or 1, if it is 1, then you have a pulse and you return to 0. Okay. If it is 0, you remain 0. So the baseline is 0, and whenever there is a 1, you have a pulse. Okay. This is RZ bipolar. That means the signal could be positive or negative, right? And it is RZ means the normal condition is 0. So the difference you are seeing here is that every time you have a 1, you are giving a pulse of different polarity. So you have a positive pulse, then for next one you have a negative pulse. Here there was a single one, so just a positive pulse. Again, you have a stream of 1. So now last one was positive, so this becomes negative, and so on. The reason why such a thing is adopted is that if you look at average voltage level, it will turn out to be 0. Okay, assuming that there are okay, even if ones and zeros are not matched, you would get, because half the ones will have a positive pulse, half the ones will have negative pulse. So on the whole, it will average out to a 0 mean level. This is NRZ, that non-return to 0. So to represent this one, signal becomes 1, and next is 1, so it remains 1, and 0 is represented by a lower level. Okay, so 1, 0, 0, 1, 0, and so on. Same thing made bipolar, and this is another one where with each one you are making a transition. Okay, so this one is represented by this transition, next one is represented by this transition, this one represented by a transition, and so on. So when there is 0, no transition. When you have 1, you toggle the bit. Another encoding. So for each one, there is a transition. Okay, 1 means transition from 1 to 0. 0 means transition from 0 to 1. Okay. So another way of looking at this is that each clock period is split between two halves. You have high followed by low for a 1, and low followed by high for a 0. So the idea is just to show that there are numerous ways in which a bit stream could be represented by a voltage level. And a differential representation means that you, instead of one wire, you use two wires. The idea of this is to provide a good noise immunity. So what happens that when a signal is traveling over wire over substantial distance, from environment, there could be some interference. There could be electromagnetic fields in the environment, which would induce some noise signal on the wire. In a differential case, you have two wires. Typically, they are carrying voltage which is opposite of each other. Okay, so if you have plus voltage on one wire, other one is carrying equal minus voltage and vice versa. So now in this, if there is an interference, if there is a noise voltage getting induced, same will get induced on both wires, right? And essentially at the receiver end, you are looking at the difference in the two voltages. So the noise induced on one wire and noise induced on the other wire, both will get cancelled as you perform the subtraction. So that is the idea of. So it costs more. You need to carry two signals, two wires, but it's possible to keep it immune from noise over a long distance. Now, uh, now imagine that you have serial transfer happening between two subsystems. Okay, I'm saying in general subsystem. One could be a processor side, other could be a device. Okay, so timing is very important, and the time information could be managed in three different ways. You could have synchronous approach where the two parties share a clock. So it is the clock, common clock, which is giving the timing, and both are working with same clock. That means they have same time reference, same frequency, same phase. Mesochronous means uh, that you are transferring clock signals either separately or with the data. So you have uh, because of the delay, the clock signal at the two ends will have same frequency, but they may be out of phase. Okay. The third is plesiochronous, where there is no clock being sent from one end to other end, but the two parties try to generate their own clock locally at the same agreed frequency. So suppose both say that, okay, the data transfer has to be with clock running at 10 kilohertz, 10 cycles per second. So they will have their own clock generator, which one may actually be 10.0, other may be 10.0001. Okay, so there could be slight difference in frequency because these are being generated independently. So we have to live with this case where the frequency is nearly same, not exactly same, and this slight difference in frequency will manifest in terms of gradually changing phase. Okay, so one clock will keep lagging the other gradually, and the phase difference will keep changing. So example of the third one is a serial port or COM port, which you might see on some system. So on the panel, if you see connectors like uh, this, okay, there may be many connectors. Typically, this is for this is a parallel port. This is for graphics. This is a VGA connector, and these are for keyboard or mouse. Okay, this is what is called a serial port or COM port, and it follows a serial standard called RS-232. This supports many different speeds, many bit rates, ranging from this to this. And so you could have serial data going from one to other and vice versa. So it happens on two separate wires. Data moves in two different directions. The clock is not going on the cable. Okay? Both generate their own clock and try to keep it close to each other and somehow take care of the phase difference. So a device which is used to interface with such a port is called UART, or Universal Asynchronous Receiver transmitted. So, for example, on the processor side, it would communicate with parallel data. So you have, let's say, 1 byte sent by processor, which is converted to serial form and sent to the device. Serial data coming from device side is converted to received and converted to parallel form and sent to processor. So universal means that this design could be such that it could support several data rates, different formats, parity conventions, etc. The term baud rate is nothing but the rate at which bits are being transmitted. So in fact, you could have a UART on both sides. So imagine two modules are there, which internally work with parallel data, but for communication, they do it over serial line, and UART would be the interfaces on both sides. So here, data line is typically at high voltage level, and beginning of actual transmission is indicated by what is called a start bit. Okay, so normally it is 1, and a 0 transition indicate that now the data transfer is starting. So for 1 clock period, you'll have a start bit, and then you have some 6, 7, 8 data bits as per the agreed format, and then there is a the stop bit. Okay, so stop bit ensures that before the next transmission, the wire is at high level, at least for 1 cycle. So in general, they could be one could agree upon multiple stop bits, 1 stop bit or 2 stop bit. So this indicates actually a gap between uh, 2 pieces of data. So now, since they have clock which is nearly same, they may be phase difference, but the phase change will not accumulate too much within one data word. Okay, but the next one could come at arbitrary time. So this gap between 2 words could be arbitrary, and the receiver has to sort of ensure that it detects this phase. So timing will start counting from this point onwards. So in fact, what may be done is that transmitter is sending data like this. Receiver works with a clock rate which is, let's say, a multiple of the basic clock, so that it keeps sampling the input line at a fast rate and is able to accurately detect this change from 1 to 0. So let's say you have a clock at the receiver end which is 16 times faster. Then with that clock, it will keep sampling, and once it sees the change from 1 to 0, it will take that as the starting point, and then it will wait for 8 more clocks to sort of come to the middle of the start bit. Then after every 16 clock pulses, it will sample the input with an attempt to sample them in the middle of the bits. Okay, because the transition points could be noisy, they could be some delays, and cleanest thing you can sample at the middle. So you try to achieve it by having a faster clock. This is another picture showing same thing. So I showed a specific sequence of ones and zeros. So it is 1 1 0 0 0 1 0 0. But in general, a diagram like this indicates that there are 7 bits. Any of these could be 1 or 0. So there is of course a start bit, and in this example there is a 8th bit which is the parity bit, and then there is a stop bit. So in fact, the data bits could range from 5 to 8 in this standard. Parity could be even parity or odd parity or maybe absent. There is invariably one start bit, and stop bits could be 1 or 2. And the data rate also follow a specific values, so 300, 600, and so on. Another example I want to take is a serial bus where the clock is shared. So SPI, or serial parallel interface, is a synchronous serial protocol, and in the FPGA board which you use in the lab, this is used to connect the FPGA board with some peripheral boards. So it has a clock signal going from master to the slave, and there are two data lines. MOSI means master out, slave in, and MISO means master in, slave out. Okay, and another signal called slave select is SS. Bar over this indicates that a 0 will be output on this to select the slave. So here there's clearly a clock. There's a chip select or slave select signal which will select, and there is a stream of ones and zeros synchronized with the clock. There could be convention that initially there may be some zeros and leading zeros and trailing zero. In between there are data bits. So again, it's a commonly understood convention of how bits have to be sent between master and the slave. Briefly, let me talk of Universal Serial Bus, USB. This is very complex, although there is a single wire, but as you see, there's a lot of complexity in this. We'll not go into all the details. Just idea is to give you a flavor of what kind of bus this is. So it's used for a huge variety of devices, and it's replacing various earlier serial and parallel ports. Okay, more and more common now. It can provide much higher speed than RS-232, which we just discussed. It is packet oriented and not character oriented. The RS-232 example which I took was character oriented. That is, there is a protocol only in terms of character. So you have 8 bits representing one character. We saw how those bits are sent. Then next character will come and so on. But here in USB, a sequence of character or data elements would be put together in the form of a packet. So there are details of how things are happening at the bit level, and then there are details of how things are happening at character level and how things are happening at the packet level. Okay, so it's a layered arrangement, and that makes it more sophisticated and more complex. Here the clock is not sent separately from data. So from the data line itself, using some special circuitry, you try to recover a clock signal. Okay, it's a differential signaling approach. So the two wires are called D plus and D minus. And it could be used to connect as many as 127 devices through hubs. Okay, so from your main box, processor box, may have multiple USB sockets. From each socket you can connect a hub, and from each hub you can connect multiple devices. So there could be several devices, and in each device there could be multiple endpoints. So endpoints refer to so within each device there could be many addressable registers you could imagine. So endpoints are where actually the data finally ends up in. So within each device there are multiple endpoints, so either sinks of data or sources of data. There are physical characteristics as part of the specification: type A, type B, type C, mini A, mini B, micro A, micro B. So there are various types of connector which are used. Each is its own. Each is a standard one. Okay, and in each you could see This type C is looking more complex, but typically you would see four these metal thing, four wires. Okay, two are for data and two are for supply and ground. Again, as you go across the standards, there is increase in speed, and speed is also referred to by this terminology: low speed, full speed, high speed, super speed plus, and so on. Okay. There are different voltage levels. So LS, FS, LS refers to low speed, FS full speed, HS high speed, and SS super speed. So LS and FS have this voltage level. So there are two ranges, 0 to 0.3 and 2.8 to 3.6. For HS and SS, you could see that the voltage levels are much lower. So lower voltages and higher speed is the correct result. Now, what
about HSLF, LSFS refer to?
These are, terms referring to the difference in speed. So you have numerical values for different speed levels.
So these are the bandwidths.
Yeah, these are the bandwidth. So in megabits per second or gigabits per second, you have these values.
It's bits per second, not bytes.
Bits, yeah. So within these two wires, D plus and D minus, you can represent many things. Okay, you of course they carry the data, but the way you switch these, you could indicate many kind of events. Okay, you have many events as you can see here. It could indicate the device is detached. So whether something is connected at the end of the cable or not, it can be detected. Okay. Device wakes up host and device idling, start of packet, end of packet, reset device to a known state, power down the device, host wakes up. So many things can be indicated just by changing D plus D minus in certain manner. So we'll not go into those details. And over these wires you carry different packets. So let me show you. The packets are different types. Again, they are data packets and they are handshake packets. They are not separate handshake wires. So it is exchange of packets which does handshake. Okay, they are token packets. So an example of how a packet is represented over these two wires is shown here. So red signal is the D plus, green is a D minus. So in the beginning, you could see that they are just going through a periodic waveform, and this is here the clock could be synchronized. So the way it is done is that everything which is connecting on USB will have a clock generator, but that needs to be kept in synchronism. So looking at this signal, which is clearly indicating a periodic set of changes, the clock generator would synchronize with it. Okay. So there is a specific convention of how many such transitions have to be seen to synchronize, and then some pattern on these is indicating start of a packet. So this is a synchronizing packet. This is a packet indicating that there is some error. So it is a negative acknowledgement packet. Okay, and then there is something which is indicating end of packet. Here, for example, you could see that D plus and D minus are not opposite of each other. Usually they are, most of the time they are, but they need not be, and that also carries some information. So we don't go into details of what actually is this representing, just to give you a flavor of what is happening. Okay, so this was some idea about buses. Let's look at specific peripheral devices, hard disk drive one, and we look at solid state drive also. So this is just an example of specification of how things would be specified for. Okay, you are talking of capacity, how many bytes it can store, the size. So the size are also standard, 3.5 inches in this case. RPM is one important specification. How many revolutions per minute is carried out by this particular disk drive? The rate of data transfer, 250 MB per second. The structure of disk. So basically, you have these rotating disks, and it's not a single disk. There are multiple disks. So in this device, there are actually eight disks which are rotating all together, and on each of these, the information can be stored on both sides. Okay, so there is what is called a read-write head. If you have seen a LP record, long playing record, these are revolving records. You may have seen gramophones. So structure is like that. So there is a read-write head which is positioned at some point on the disk surface, from where it is either writing stream of bits or reading stream of bits. So for each disk surface, there is a read-write head. And the information is organized in terms of tracks which are circular, and on each track there are sectors. So there are what are called physical sectors and logical sectors. Physical sector is they are physically separate regions on the track, and within each physical sector there is a logical division into much smaller sector. Okay, size of sector is indicated here, and there is a density of information. How many bits are there within 1 inch? So it is kilobits per inch. And the second figure is saying kilo tracks per inch. How closely spaced the tracks are. And the last one indicates the presence of cache memory here, where the data is data read from the track, for example, could be put in that memory, and from memory gets transferred to wherever it has to go to. Okay, so it's a local memory acting as a cache. Here is an interesting comparison which I have picked from Wikipedia. It's indicating, it is showing several parameters pertaining to disk drives with an interval of something like 6 decades. Okay, so how a disk in 1957 looked like and how it looks today. So in terms of capacity, you have 3.75 megabytes and 18 terabytes now. The last column is indicating the factor of improvement. The volume improvement here in case of volume is in terms of miniaturization. So how much it has reduced. So here you're talking of meter cube and centimeter cube. Weight in terms of kilograms and grams. Access time in hundreds of milliseconds. Here it is in milliseconds. The price 9.2 USD per kilobyte. Here it is 24 USD per terabyte. Density in bits per kilobits per square inch. It is terabytes per square inch. And last one is mean time between failures. So reliability from 2000 hours to 285 years. So reliability is extremely high. If you see the improvement factors, where is it you see the largest factor? It's in terms of information density. Okay, in overall capacity, there is a slightly lower improvement because the size has also reduced, right? And the least improvement you see is in terms of access time. Access time is also related to the speed of rotation, and that being mechanical, uh, there hasn't been such a dramatic increase in speeds there. So this is a picture of a disk drive. You could see that you have multiple platters here, multiple disks, each storing information on both sides. And what you see is a read-write head. This read-write head moves across tracks. Okay, it is pointing to some circular track which is around here, and if it moves outwards, it will point to a different track. The disk rotates, and it's right now looking at information which is at this point. And as disk rotates, the head effectively moves along a track. So in this, you could have 1 to 4 platters, each with 2 recording surfaces. Rotational speeds vary in this range, 5400 to 15,000 RPM. Another closer view, you can see multiple platters, and this is read-write head. So number of tracks could be some tens of thousands. Sector per tracks, bytes per sector. Seek time. Seek time is the time taken to go from one track to other track. Okay, it would be in the form of fraction of millisecond or a few milliseconds.
So in this case,
Yeah.
the track refers to as concentric circles, right?
Yeah.
And then what will be the sector here?
Sector is just some area on a single track.
Is some part of it.
Yeah. So sector also determines the unit of information which gets transferred. So you will read one sector at a time. I should say at a time. I should say in one go. In one go, you read one sector, then next sector.
It's like a block.
It's like a block. Yes. So the virtual memory pages also would be related to sector. So each page would be integral multiple of a sector typically. So here I was talking of track to track movement time, and average is that in one seek you may move several tracks. So this is kind of average.
So, so what do the heads perform on the magnetic disk? Obviously, they can't be physical elements.
Don't hear you clearly. What is?
So, what are the heads performing on the disk?
So each head is able to read one or write one bit at a time. So as the head is assume that normally head is stationary, and as the disk rotate, head moves within a track. So from a track, it will read a sequence of bits as the disk moves. Okay, so if you're done with one track, then you move to another track. You're done with that track, you can move to another track. So suppose at some point of time, the head is positioned somewhere, and you want to start reading from a particular track. So you say that I want so many sectors to be read from so many tracks, from track number so and so. So initially the head has to be positioned on that track, and then knowing which starting sector you want, the disk when the disk rotation leads to that sector being in phase with the read-write head, then the reading or writing would start. So before you actually start reading or writing, some mechanical movement is involved. One is that the head has to reach a particular track, okay, and the disk has to rotate by a certain angle so that the head gets positioned on the correct sector within the track. All right.
All right.
So what we need to know is the average seek time and average rotational time. So normally you'll say that on the average disk will rotate by half a circle before you start reading. So in best case, you may not need to rotate at all. In worst case, it may be almost a full circle. So average is like half circle. So the disk latency is sum of seek time, rotational latency, plus data transfer time, plus some time the controller may take. So there is a disk controller sitting there which manages all this, and there may be some cycle spent in that. So normally controller overhead would be typically smaller than other latencies. So average rotational latency, as I mentioned, is the time for half rotation. So if you know RPM, number of rotations per second, sorry, per minute, then you can calculate this. So if you are specifying RPM in, let's say, how many thousands of rotations per minute, then you can, this factor of 60 is to account for number of seconds per minute, and this 1000 is to get you in milliseconds. Okay? And half is for half rotation. The data transfer rate could be typically of the order of a few tens of megabytes or hundreds of megabytes per second. And then there is seek time, which is again in terms of milliseconds. Alternative to hard disk drive like this is flash, okay, which is semiconductor memory like SRAM or DRAM, but it is non-volatile. So in that sense, it is like magnetic disks which are non-volatile. Non-volatile, as I mentioned earlier, means that when you turn the power off, the information is not lost. In SRAM, DRAM, it is lost. Its latency is much faster, much less, okay, because moving parts are not involved. So it is size-wise smaller, lighter, more power efficient, and more shock resistant than disk. If you have ever experienced your laptop with the disk drive falling, the disk can get damaged. Okay, so there is often an arrangement that there is a accelerometer in the laptop which will detect a certain change, certain movement, and it will park the disk. That means the heads are retracted in a parking position so that heads don't, the read-write heads don't, clash against the read-write surfaces. So there is some arrangement for preventing that accidental damage, but still, if impact is larger, it may not really prevent disk getting damaged. But these are the solid state drives are much more resistant in terms of shock. In terms of capacity, these are lagging behind but trying to catch up. However, these could be more expensive for same capacity. The main negative part about solid state drive is that they wear out much faster than hard disk drive. Although these are not mechanical, but the circuitry would get damaged with time. So there is a wearing out effect. Flash memory is made up of what is called floating gate transistors. So it's a semiconductor memory. Floating gate transistors are able to store information in a non-volatile manner. Reading is fast, but writing is slow. It requires larger current, and that can change slowly. Usually, writing involves a one-way state change. For example, so it's a matter of convention whether you consider it 0 to 1 or 1 to 0. So suppose in the normal state, all bits are 0. Okay, so writing into flash memory would mean changing from 0 to 1. The process of changing from 1 to 0 is called erasing. Okay, so you need to erase previous information, making it all the bits 0, and then wherever you want 1, you write ones there. Okay, so the process of erasing is slower, and it is done in bulk. That means many bits are simultaneously erased. It's a block erase. Okay, so entire block gets erased simultaneously. Unlike the EEPROMs where so you have those where you can erase every bit, or you can erase the entire memory chip altogether. Here it is, the blocks are formed and one block gets erased at any given time. This is the structure of a floating gate transistor. I will not go into physics of this in detail. All you can see here is that this is the oxide area of the transistor, and there is a floating gate. It's not connected to any external terminal, whereas you have drain, gate, and source, which are connected to external terminal. But when a current is passed through this channel is between these two N plus areas, then some charge, some electrons get trapped on this floating gate. Okay, and they remain trapped even if the current is no longer passing through. That is how you have a permanent storage here. Okay, circuit wise, you show a transistor of this kind as shown here. So when the electrons are not trapped here, it behaves like a normal transistor, normal NMOS transistor. And after the electrons get trapped, this is a transistor which is turned off. So such transistors can be arranged in two different configurations, NOR flash and NAND flash. The structure of NOR flash is like NOR gates, that is, such transistors are put in parallel, and NAND flash where they are put in a NAND-like structure, that means they are in series. I'll show pictures of these. NOR flash allows random access, whereas NAND flash allows sequential access. Partially random, partially sequential, because they are put in a series, there is some kind of sequential access. NAND flash gives you higher storage density compared to NOR flash, and it is less expensive. So NAND flash is used for pen drives, SD card, solid state disk drives. Okay, solid state drives, because of its higher density, and the sequential access can be tolerated here. In so you have some memory used for booting. Okay, that is NOR flash, because that has to be randomly accessed like normal SDRAM, normal DRAM or SRAM. So this is a picture of NOR flash. You can see that all these transistors are, one end is ground, other end is all connected to a common wire. In NAND flash, they are put in series. Okay, so you need to activate these one by one to see which one is containing 0, which one is containing 1, and that's why sequentiality creeps in. This is a picture of a USB flash drive opened up, and inside you can see that there is a one is a flash chip, other is a controller. Now let me take an example which will show the operation, IO operation, and how performance limits of individual subsystem will affect the overall performance. So if you keep focusing on processor only, IO performance may often get neglected. So it's important to look at IO performance also. For example, if a benchmark is having a certain IO activity and certain computational activity, and if you improve the processor, suppose now you look at how CPU has been improving over the years, and every year, let's say improvement is by 50% in terms of speed. Over 5 years, there has been a improvement which is like 7.5 times. Okay, if IO has remained unchanged, which is largely the case, then the overall performance, now recall the Amdahl's law, IO part remaining change, it is only the 90% which is reducing. The overall performance wouldn't have improved by the same factor. Okay? The overall improvement comes much lower. And if you are considering a program which is IO bound, then improvement is much smaller. There could be, again, different definitions for IO performance. It could be throughput related or in terms of response time. Okay, so time related or speed related. You could talk of data transfer in terms of kilobytes or megabytes per second, or total number of IO operations. Each operation would involve certain data transfer. You in interactive systems or embedded system, response time may also be important, and you need to look at the IO response time. In some cases, both are important. This shows that requirement may be different in different scenarios. Supercomputer, you would be interested in a lot of data which is required. There is typically more output and less input. In transaction processing, transaction per second, response time, both may be important. In a file server, file operation per second may be important, and so on. There could be sometimes discrepancy in units. You know, in memory, invariably, when you talk of 1 KB or 1 MB, we are talking of 2 raised power 10 or 2 raised power 20, which is not exactly 1,001 million. It's a little more, as you can see here. In IO, you might often talk of 1 KB per second, 1 MB per second for exactly 1,000 bytes or 1 billion bytes. Okay. So unless specified clearly, there is a room for some discrepancy. Okay, now let's suppose you are given a server which has to carry out some IO intensive application, and there are certain application characteristics given. What we like to find out is the maximum sustainable performance for the given characteristics of processor, memory, buses, and IO devices. And we'll do that, we'll find in terms of the rate of IO operations per second. So specific server is taken in this example, which has 8 processors across 2 sockets. A socket means that where a processor chip is plugged in, and within, in this case, each socket can take quad processor, each having 4 cores. There is a certain amount of memory which is connected, which is following certain DDR standard. This is particular standard. We 667 is referring to clock frequency, 667 megahertz. And this memory is distributed across 16 dual inline memory modules. FB stands for front side bus. So they are connected through front side bus. There are 8 hard disk drives in the system. The size is there. RPM is given. And the capacity is given. The interface standard is given. The Ethernet ports, there are certain PCI Express buses and there are certain USB. Not all information is relevant. So it's a server configuration which is given. And in terms of picture, it looks like this, that you have memory controller hub and IO controller hub. These are, in Intel's terminology, these are called North Bridge and South Bridge. So on memory controller hub, on one side you have processors connected through FSB, front side bus, and on other side you have memory modules and connectivity with the South Bridge hub. Okay, so two different types of connections are there. Plus there are some PCI Express buses coming out of this also. This one, the lower one, is mainly providing multiple buses of different types. Some of these are connected to disk drives and some other peripherals. Okay, so now what is the kind of application we are trying to run? We are running a program which requires lots of IO operations, and the processor executes so many instructions per IO operations. Okay, so not only user programs spend some instructions, there are 100,000 instructions executed by OS also. So this involves basically initiating the process and then looking at the final result. So on the whole, so many instructions are executed to carry out the operation. The workload consists of 64 kilobytes of data to be read from disk drives. Okay, so when we say one IO operation, it means reading 64 kilobytes from some disk and putting in memory. Each processor is able to sustain 1 billion instructions per second. So that is a processor speed given. We need to find out maximum sustainable IO rate for a fully loaded server, Sunfire server, in two different cases, for random reads and for sequential reads. So we'll see, I'll tell you what is the difference between these. We assume that there are multiple disks and all the requests for reading are actually spread across different disks. Okay, so if, let us say, if there are simultaneously you have 4 blocks to be read from disk, then they can be read from 4 different blocks. So there are no disk conflicts. That's an assumption here. So we one by one we try to find the speed limit of each subsystem. So processor has to execute certain instructions. 200,000 in user program and 100,000 for OS. Okay. So the rate of execution of instruction is 1 billion instructions per second. So you can take the ratio of these two. You get 3333 IO operations per second. So since processor involvement is there at some level, you cannot have more than these many operations per processor. So one socket has 4 processor. So 4 times this is the capacity of one socket, and there are 2 sockets. So multiply by another 2. So many IO operations per second. Now let's see from the disk side. Time taken per IO for disk is seek time plus rotational time plus transfer time. Okay, we are ignoring the controller time here. So suppose seek time is given to be 0.725 milliseconds on average. Rotational latency, knowing the RPM, we can find the time for one rotation. So let's say that turns out to be 2 milliseconds. And 64 kilobytes transferred at the rate of 112 megabytes per second. So that is given. We add all these, it adds up to 3.3 milliseconds. That means each disk can do. So since it is millisecond, we have 1000 factor, 303 IO operations per second, right? And if you have 8 disks, you can do 8 times that. Now this was for a random access. That means every IO would require you to move randomly from one point on the disk drive to other point, involving certain latency, seek latency and rotational latency. But if access are sequential, that means you are reading one track, you are reading one sector on a track, then immediately next sector on the track, and then next sector on the track, and when you finish that, you just go to consecutive track and so on. The rate is bound by just the transfer time. Okay, so we are not incurring any seek time and rotational latency. So 64 kilobytes divided by 112 megabytes per second gives you 1750 IO operations per disk. Okay, so multiplied by 8, you get for 8 disks. Now the data has to go through PCI Express bus. We need to look at the bandwidth of that. So bandwidth of each lane is given as 250 megabytes per second. For 8 lanes, it will be 8 times, which is 200 megabytes per second. And each IO operation requires 64 KB to be transferred. So we can, this throughput in terms of megabytes per second can be transformed into number of IO blocks transferred, which is 2000 MB per second divided by 64 kilobytes, or you get 31,250 IO operations per second for 8 PCI lanes. Now, memory limitation. Memory is running with a clock of 67 megahertz, and there are 8 modules, so you get that much. Dividing this by 64 kilobytes, you get number of IOPs. One memory module, these 8 memory modules can sustain. So it's 83,375. Maximum number of DIMMs could be 16, so you can have actually 2 times. This was for 8, so you can have 2 times this. FSB has a limit of 10.6 gigabytes per second. So that is a peak bandwidth. Sustained bandwidth, we take half of it. And again, dividing by 64K, you get 81540 IO operations per second. And there are 2 buses, so we get twice this. Putting all these together, we can see how the overall picture emerges. The capacity of 8 processors is this much. 8 disk drives is this much for random reads and 14,000 for sequential read. 8 lane PCI Express gives you this much. Okay, one front side bus DIMM gives you 83,375 IO operations per second, and one FSB gives you 81,540. So once you have seen the limitation of each, you can see where is the bottleneck. Okay, if you want to do random reads, then you are limited to only 2425. But on the other hand, sequential read, again, disk is the limitation. So 14,000. So therefore, the bottleneck in this case is disk, but that may not always be the case. Okay, I think I'll stop here. If you have some questions, I can answer those.
Sir, what is meant by this seek time and rotation time?
Seek time is the time required to move from one track to other track. So that is the movement of the head. And then there is rotational latency, which is the disk has to come, rotate, and the required sector has to be in interface with the head. So head moves only radially, moves from track to track. But different tracks get accessed because of rotation of the disk.
All right. Okay.
Any more question? Okay, then I'll close now.